Hi, this is going to be lecture 14, where we talk about weight, that's the force of gravity, and normal forces. So we'll come to understand the force due to gravity, that's what we call the weight, and we'll do so by going back to looking at free fall examples. And we'll notice in the process that mass has a special dual role in mechanics, namely that it comes into Newton's second law. It's what's called inertial mass, but also determines the strength of the gravitational force. And that's a very philosophical, deeply interesting issue. We're going to touch on it only briefly, though. We'll then talk about normal forces, what they are and their properties. They're very important. They're all around us. And we'll explain their properties by imagining to zoom in to the atomic level, the atomic structure of objects. It's going to be a bit rough. We're not going to be very careful here, but we're going to get the general gist of it. We'll look at some examples, of course, and finally, we're going to discuss what we mean by weightlessness. When you feel weightless, for example, what do you actually feel? Alright, so let's get started on those. So let's imagine there's a rock, and the rock is falling. Now, the rock is falling, so we imagine it has a acceleration, we draw with double arrow, of magnitude g downwards. Now, it doesn't matter if the rock right now is going up or down, right? If it's just falling in air, we can ignore air resistance. It's going to have an acceleration g. Okay. Now, given what we know about forces, well, what is this telling us? Well, if the acceleration is g, right, by 9.8, 9.81, or depending where exactly on Earth you are, so there we go with 9.8 meters per second squared, or 10. Doesn't matter if you're on a different planet, a very different value, of course. That's the acceleration. So, but we know that the acceleration is equal to the net force divided by the mass. Right, that is Newton's second law. Write it out. Mass. Right, this is Newton's second law. Let me abbreviate this Newton's law number 2. So, acceleration is g, but the acceleration is given by this. And what's the net force? Well, here, if gravity is the only thing that's acting on it, there's no other interaction, then the net force just is gravity, or is the weight. Force due to gravity, call that the weight. Weight of an object, the force on it due to gravity. So putting these pieces together, we see that, well, acceleration, the g, right, g is the acceleration, g is the weight divided by mass. And so the conclusion we must come to, therefore, is that the weight is equal to, so this is the weight, because the net force, the only force acting is the weight, so that's the net force, is acceleration times mass. But acceleration is g, so that's mass times g. And then that's going to be the important result here. So we want to distinguish very carefully here between the notion of weight and the notion of mass. Because in daily life we tend to sort of conflate them, and again, that's not something I want to criticize, right? It'd be wrong to call out your great-grandma at the dinner table for using weight when she means mass, right? Unless the context is physics. And if your grandma is a physicist, or great-grandma is a physicist, she better get us right. But the point is, in daily life, we don't really distinguish between those carefully, and that's okay. But in physics, they have a very specific meaning that we have to be aware of. So the mass is just how much stuff there's. We kind of discussed it already. That's going to be in kilogram, right? The weight is a force, right? So this is a property. Mass is a property of the object, but weight is a force, so it's going to be measured in newtons. It is the force due to gravity. So one is a force, an interaction, the strength of an interaction. One is an inherent property of the object. Because we live on Earth, where G is always the same, we sort of can get away with conflating them, right? But you can't conflate them if you go out into space, say, right? If you go into space, far away from any planet, you won't have any weight. There's no force due to gravity. You still have exactly the same mass that you had before. So it's a very important distinction. Don't confuse them and read problems carefully, right? Write this on. So read problems, etc. Problems, etc. carefully. Tell you, is it talking about mass? Is it giving a mass? Is it giving a weight? What is it asking for? Don't confuse the two. Okay. So let's just quickly plug in some examples. Say here's I am me, your instructor. So examples. Your physics instructor is about 80 kilograms on a good day. Instructor. Mass equals 80 kilograms. Right. So 180 pounds, if you must know. 80 kilograms. So what's my weight on Earth? On Earth, G is 9.8. I'm going to go with 10. The weight is going to be 80 kilograms times 10 meters per second squared, which comes to 800 newtons. So kilogram meters per second squared, that's 1 newton. Now, if I go to Mars, I still have a mass of 80 kilograms, but my weight has changed. Weight on Mars. Well, on Mars, G is only about 3.7 meters per second squared, not 9.8. It has a smaller, Mars has a much smaller mass than Earth, and so its gravitational pull is smaller. And we'll talk about exactly how much smaller and how to calculate that later in the course. Right now, we'll just take this as a kind of measured, experimentally established result. So in that case, the weight on Mars is going to be the mass, m, which is the same, 80 kilograms. But G is now just 3.7. And now, what does that make? Now I have to think for a moment here. This makes in my books, let's have a look, something like 296 newtons. I feel like my brain feels a bit rusty today, something like that. So a lot less. So I weigh a lot less on Mars than on Earth, even though my mass is exactly the same. This is for example 1. The next example is the aforementioned potato. So a potato has a mass of maybe 100 grams, 0.1 kilograms. So that means its weight on Earth, and I'm just going to write weight if I don't specifically say another planet. The usual implication is it's on Earth. Right? Assume stuff happens on Earth unless you're told otherwise. Weight would be 0.1 kilogram times 10 meters per second squared. Well, 0.1 times 10, that's just 1 Newton. Okay. So take a note then of this. Gravity is the only force whose strength depends on the mass of the object on which it acts. This makes gravity a very special force. There's no other force that does that. There are things like, say, electrostatic forces. They depend on the object on which they act, namely on what's called electric charge, so a property of the object, but not on the mass, for example. Or when we talk about friction, perhaps, friction is going to depend on the roughness of the surface. Hopefully already kind of visualize that. The roughness of the surface. So the properties of the object on which it acts, yes, but not specifically on the mass. Whereas gravity is the only force that seems to, whose strength seems to depend very directly on the mass. This makes gravity very special. So this is one thing to say. So gravity is special. And mass seems to have this strange sort of dual property. Has a dual role to play in mechanics. So the first thing it does is it determines the resistance to being accelerated. Right? This is the mass in Newton's second law. Resistance to being accelerated. Right? A is the net force divided by the mass. So bigger mass, lower acceleration. So the mass of an object determines how hard is it to make it go. But then, as we learned just now, the mass also determines the strength of the gravitational force. Namely that the weight is equal to m times g. Now the result is, from those two facts, is that if I plug in the weight for the net force, like if the weight is the only force acting, then the masses are going to cancel and everything's going to have the same acceleration, namely g, right? So I take this, plug it in here, well then the m here is going to cancel with this m, and I'm left with a equals g. So everything falls at the same rate, which we kind of observed before. We observed this experimentally. So those two appearances of mass, they're conceptually very much independent of each other, right? There's no inherent reason, at least not from the point of view of Newtonian mechanics, that the property of an object that determines how hard it is to make it go should be the same as the property of an object that determines the strength of the gravitational force. And indeed, as I said, gravity is the unique force that does that. We give those two roles names. So this m here is called the inertial mass, and this m here determines the weight is called the gravitational mass. Notice that I'm not saying that those are different masses, like different values. No, I'm saying they are conceptually different roles, and so this kind of inertial, gravitational, those two roles that a mass, the notion of mass plays. And the big mystery is, well, why is inertial mass the same as the gravitational mass? And indeed, people have tested this. People have done experiments to test, are those really the same, with extremely good precision. Or, you know, maybe are they like, is this like 1/1,000,000th bigger than this one? Like, this is 1.000000001 times this one. Right? And the answer has always been no. The answer is always no. Look, these are exactly identical. So why are those two the same? Seems to be a mystery. And indeed, it was a mystery for about over 200 years, from when Newton came up with his theory of mechanics and so wrote it down in full, to the advent of general relativity, which is a more sophisticated theory of gravity that ultimately explains this. And it explains this by getting rid of the force of gravity and replacing it by deformations in the geometry of space and time. But that's a much more advanced topic that we're not going to be able to cover here. You probably have to wait until maybe your last year of studying physics as an undergrad, or maybe even you have to wait until you go to take some grad courses in physics, if that's the path you want to follow. Alright, so I leave it as a mystery to think about. You might want to first think about, okay, what is really going on there? What is this mystery? What am I really asking here? So I want to just demonstrate this though, this difference, with a very simple example. An example is, imagine we kick a ball on the moon. Actually, let me get a new page. Kick a rock, say a big rock. So care if you go to the moon. Kicking a rock on the moon. Okay, here's my picture. So imagine you go to the moon, you and your astronaut friend, and you're going to lift a rock. Right, now you lift a rock, you can lift really, really heavy rocks. The reason you can lift heavy rocks is because to lift something, you have to overcome its weight, and the weight is a lot less on the moon, because g is only 1.6 thereabouts, so 1.7, something like that. Meters per second squared, right? So I can lift really heavy rocks. So on the moon, you can lift about 6 times more. Right? Because gravity is about 1/6 of the strength, meaning everything is 1/6 of the weight it has on Earth, so I can lift a rock that's 6 times as heavy as the rock that I might be able to just barely lift on Earth. So now your friend sees you lift that rock, and they're like, alright, that looks like fun, let's play a game, and starts kicking this rock. And then he breaks his toe. Why does he break his toe? Well, because what hasn't changed is the inertial mass of the rock. So the inertial mass has not changed. Now, of course, the gravitational mass hasn't changed either, because they're the same. But what has changed is the weight, because g has changed. The reason I'm saying inertial mass here is because that's the relevant one to kicking something. Right? So if you hit, if you kick that rock, your friend kicks that rock, well, he's gonna get hurt. But inertial mass has not changed, so rocks still as difficult to accelerate as on Earth, or anywhere else really in space. Right? So don't do this. When you go to the moon, yes, lift heavy stuff, but don't get over ambitious and try to start playing football with giant rocks, right? Because it's gonna hurt you just the same as if you were kicking a heavy rock on Earth. All right, just a safety warning there, I suppose. Now, just a final remark here. While we're talking about weight, this is the positive remark. So weight, right? Weight is independent of everything else except the mass and the strength of the gravitational field G. Weight is independent of everything except M and G. So this is what planet are you on, really, right? Now, what that implies is that if you have some kind of problem, trying to solve some situation, lots of forces, trying to figure out what's going to happen next, well, the weight is usually what first thing you can just write down, because you know what it is. So that implies that weight, often the easiest thing to write down. Right? Because no matter who's pushing whom, what is friction, air drag, who cares? Well, you know what the weight is. right? It's m times g. It's very straightforward. All right, now that's enough about the weight right now. Let's move on to the notion of a normal force. Imagine the following situation. I've got a textbook that's sitting on a table, so I've drawn it here from the side. Now we know at this point that because we assume this is on Earth, there's a force of gravity on it. We know what it is, so I'm just going to draw it. Force of gravity called the weight, acting downwards, of course, and that weight is equal to the mass of the book times g. So why then is the book not falling? Right. So that is the big question, this big mystery here. Why is the book not falling? Because the way I've drawn it here, right, there's one force on it acting down, so why isn't it accelerating downwards? Well, you might say because the table is in the way, it can't start falling down, right? So, but saying the table is in the way, well, that does, I mean, are you saying when there's something in the way, Newton's laws no longer apply? No, it's not what we're saying. So when we say the table is in the way, what we mean in terms of forces is that there's a normal force acting from the table on the book. By normal force we mean a force due to the contact of two surfaces pushing against each other. Normal force between book and table. Of course, the normal force acts both ways, right? It's an interaction, like every force. I specifically care about the force due to the table on the book, and it's going to be upwards like this. And it is what's going to stop the book from falling through the table, right? Now, these normal forces, you get them pretty much every time the surfaces are touching, unless they're sort of touching super loosely, so if they're like by chance next to each other. Very unlikely. If two surfaces are touching, chances are there is some normal force between them. Some of the properties of these normal forces, write this down, properties of normal forces. Is this. One is that they always act perpendicular between the surfaces. So perpendicular to the surfaces. Perpendicular to the touching surfaces. So I'm not saying the normal force is always straight up. Definitely not. That would be wrong. We often encounter situations where there is an upwards normal force, but we also encounter lots of situations where normal force points in some other direction. It just depends on what is the orientation of this surface here where they're touching. Right? And this fact that they're perpendicular, that's where the name comes from. The notion of perpendicular is also called normal in mathematics. Normal. So in mathematics, we can say things are perpendicular, things are normal to each other, things are orthogonal. So there are all these different words, essentially meaning at 90 degrees. But that is where the term normal force comes from. Like, they're not normal because they're everywhere, even though they are. Can't really get away from them, or you start falling right to the center of the Earth, like where this very second. But they're normal in the sense of at 90 degrees to the touching surfaces, right? So this angle here is 90 degrees between the force and the surfaces that are touching. That's the first property. That's what they're called normal forces. The second one that's important is they always are as strong as needed. I'll show you what I mean by that in a second. As needed to stop the things falling through each other. Or to stop different things from occupying the same physical space. right? Because if the table's there, the book can't be there. And the table's gonna do whatever is necessary, or the normal interaction between them is gonna be whatever is necessary to stop the book and the table from being in the same physical space, right? It just doesn't make any sense. It's not some kind of ghostly appearance that can get stuck inside a wall. Right? These are physical objects. Alright, the strongest need, of course, there's a limit. The table might break, right? If I keep stacking books onto it, maybe eventually replace my books with heavy lead blocks, well, there comes a point when the table might just break. Or until one object breaks. Okay, so let's just look at some very simple examples of this type of scenario. Here's number one, the one we just looked at. I imagine it's a 2 kilogram book. It's resting on a table. Well, let's find the normal force. I'll just quickly draw it again. So I'm going to do my free body diagram. The weight is down, and the weight is mg, which in this case is going to be 2 kilograms times 10 meters per second squared. I assume it's an earth. I haven't been told otherwise. That's 20 newtons down. The normal force is going to be up because the table is horizontal. Normal force. Sometimes we can give the normal force a symbol. We might say, so I like to use F subscript N for normal force, the normal one. Or you might sometimes see it written like a little lowercase n, like our textbook does this. It's, you know, a different choice. We don't tend to use just a capital N because that looks like newtons and it gets confusing. But you also just always write it out, right? There's nothing wrong to doing math with words. So what is this normal force? Well, because the book is at rest, so book is at rest, that implies the net force is 0. That must imply the two forces must be equal in strength. Normal force is equal to the weight in strength, in magnitude, is equal to 20 newtons. That's very, very straightforward. Okay, that's another example. In the second example, imagine the situation is exactly as number one. There's a book, the same book sitting on the table, but now I'm going to push down with my hand with a strength of 30 newtons. So I'm kind of leaning on the book. Hopefully you can visualize that. Let's draw those forces again. The weight does not care, right? That is crucial. The weight is still what it is. It is still mg, which we know in this case is 20 newtons. The new force that we have is the force due to the hand. I mean, this is 30 newtons, so I'm going to draw it a bit longer, like this. I'm not sure what to call the force due to hand. It is also a normal force, right? Because it's like the book stops my hand from going through it, and vice versa. So, but I can just call this the force F hand. Let's write it like this, and we know what it means. Force due to the hand, and this is just given as 30 newtons, so there's nothing to calculate here. Now, they're both acting down, and then I've got a normal force. Normal force still points up because this is a normal force between the table and the book. And of course, normal force again cancels out. Same logic as before. Fn, let me write it like this time. Fn is equal to 30 newtons plus 20 newtons. Cancels out both. That's equal to 50 newtons. You can see if I were to push a lot harder, maybe with 3000 newtons, this would be a much bigger number, or maybe it'd be too big in a table, would break. Okay, so let's figure out actually why is it that a normal force can kind of adapt. Like, what's so magical about a normal force that it allows itself to just be as strong as needed? To do that, let's look at the microscopic structure of the normal force. So let's zoom in to the microscopic structure. What am I doing? Microscopic structure. So imagine this. Imagine here's my table, and here's my book. And we're just going to zoom in right here. And we're going to make this a lot bigger. Zoom in right there. So what would you see in this case? So here's the surface of the table, and the book is sitting on top of it. I'm sort of going to do it not to scale. It would be hard. Now, what's going to happen as the book goes down is the table itself is made of a lot of atoms, molecules, right? Now, I don't know what the structure of the table is, the exact molecular structure. I don't really care. I'm going to draw it like little triangles here. I pretend maybe it has this sort of triangular structure. It's entirely made up. Could be something very different. But the point is, we zoom in, and what we see is this atomic structure, some kind of pattern, right? And some kind of lattice that's more or less regular. So as then the book comes down, it's going to push down against those atoms. Now these bonds between them, they act a little bit like little springs. So what's going to happen is this. I'm going to have the book here, and it sort of pushes into the table, and it's going to compress the springs underneath it. Somewhat maybe like this. It's a little squished here. You get the idea, right? I'm not going to draw every last one of those. But you see kind of what's going on, right? So right underneath where you put the book down, it's getting squished. Over here, it's a bit less squished, a bit further apart. And it's the squishing of those springs, those atomic springs, that this was pushing back, right? The table tries to go down, and at a very microscopic level, what you would see is, sorry, the book tries to go down. At a very microscopic level, what you would see is that the electrostatic or electromagnetic repulsion between the individual atoms here and here. That's what actually pushing them apart. So they're not actually literally touching at the atomic level. There's not really any such thing. But there's always some distance between them. And so this is pushing down. They're pushing back. They get squished in the process. And if this thing is heavier, it'll push down more. Well, that means that the springs get squished more, and as they get squished more, they push back harder. So eventually, you reach that balance where they're exactly the right strength, where they push back with the right strength to balance out the weight of the object or the force downwards on the object above. Right, so imagine a little bit like a trampoline. Like you put a book on a trampoline, the trampoline is going to sort of sag down a little bit, and the heavier the object you put, the more it's going to sag down. But eventually, because it's sagging down more, the force gets stronger, the elastic force gets stronger, so it's pushing back harder. Eventually, you reach a balance. And that is how the normal force ends up being effectively as strong as needed. This is a very, very rough picture, right? This is not literally what a table looks like, not really clear triangular lattice. But it gives you the basic idea of what normal forces actually are. Now, you can't see this deformation, right? The table gets squished by a distance that's too small for you to see. Right? It's really at the scale of atoms. But that explains how normal forces can adapt to always be the strength that they need to be. Unless you push too hard, you break those springs, they can no longer support it, the atoms fly everywhere, you've broken your table on which the book sits. Alright, let's do just a couple more examples while we're at it. Here's our next example, example number 3. While roller skating, you push off the edge of the rink, obtaining briefly an acceleration of a equals 3 meters per second squared. That's like shown here. So this is, the edge you're pushing off this way. For, not maybe just a fraction of a second, you're going to have an acceleration that is, say, 3 meters per second squared. And you're going to imagine your mass is 60 kilograms. Okay, so what forces are acting? Well, we could start with the weight, right? And the weight is indeed going to be acting. Let me draw a free body diagram over here. Just the weight down. And the weight is going to be equal to mg, so we know what that is. 60 times 10, that's 600 newtons. Then there is a normal force between your skates and the floor. Right now, how much on each skate? Actually, it's a slightly more complicated problem. But the total is going to cancel it out because you're not accelerating upwards or downwards. You're going sideways. So this normal force here, so normal force with the ground, well, that's just going to be equal to 600 newtons because you're not moving up or down, you're not accelerating up or down. But then there is a sideways normal force because you're pushing off. So the force between your hand and the edge here where you're holding on. I wish I give myself more room. Live and learn. So this is let me call it the normal force with the railing. What is that? Well, that's the only force to the side. That's the force that's causing this acceleration. So the normal force with the railing is equal to, well, if it's the only force, well, it's going to be equal to the mass times the acceleration by Newton's second law, because we know a is 3 meters per second squared. There's going to be 60 kilograms times 3 meters per second squared, and that is 180 newtons. Right, so 3 forces acting here. There's a weight, because this happens on Earth. 0G roller skating, probably a thing of the future. We don't have it yet. So there's weight. The weight gets cancelled out by the normal force from the ground, because that is up, right? This is here the contact surface is vertical, so the force has to be horizontal. Down here the contact surface is horizontal, so you can have a vertical normal force. This one supports you, stops you from falling downwards, but the thing that makes you go sideways, that is you pushing off here, is a normal force between your hand and the edge. Okay, so another example. Here is our next example. We have a watermelon falling from some height, presumably. It hits the ground at 20 meters per second, so we really don't want to get hit by that. And then it hits the ground, slams on the ground, and it comes to rest, presumably not in one piece, within 0.05 seconds. So we're going to figure out what's the force on it. In fact, we're going to figure out what's the normal force during that time. So let's draw this. Here's the ground. Here's my watermelon. Just as it's hitting the ground. It hasn't splashed yet. So what do we know? We know the acceleration. Well, we don't know that yet. We can figure it out because we have a speed and a time. What we know is the acceleration is up, though, because it was moving down. And now it's stopping. Right? So downwards velocity coming to 0 means we need to have an upwards acceleration that cancels out the existing downwards velocity. But we don't know how much that is yet. So let's figure it out. What force is acting? Well, this thing still has a weight. Even during the moment of impact, it has a weight that's equal to mg. I just didn't write weight here, just wrote mg. I sometimes do that when I'm feeling a bit lazy. Because if we see mg, and it's not a unit, meaning milligrams, right? But m mass times g, we know that is the weight. So I think I can get away with that right here. But then because the acceleration is up, we know already the normal force must be a lot bigger. Don't know how much bigger, probably a lot bigger, because it's coming to rest within a very short amount of time, 0.05 seconds. But I don't know how much bigger, so I'm just going to draw it somewhat bigger. Normal force F subscript n. So here's what I know. I know that the acceleration is upwards, and actually I can work out what it is. And then I can set it equal to net force and use that to figure out the normal force. Let's do this. So A is equal to the change in velocity divided by the change in time. How long it takes, right? Hopefully you remember that. So we're going from 20 to 0. The change is 20. And if up is positive, then we went from minus 20 to 0. So I need the plus 20 of a change divided by 0.05 seconds, which in my books comes to 400 meters per second squared. So that's huge. You can call this 40g, because it's another way you often hear accelerations of forces expressed is in terms of g value, g forces, g values. That's just saying, well, how many multiples of standard gravity is it? Like this is 40 times little g. This is the sort of convention. You hear things expressed that way. Either way, 400 meters per second squared. So now we can figure out what the net force is, because we know the acceleration. The net force is going to be equal to the mass times A. Now the mass, we're told, is 4 kilograms. It's 4 times 400. That is 1600 newtons. Okay, so is that a normal force? Not quite, because the net force, we know, is equal to the sum of all the forces, and one of them acts down, so I have to actually add them carefully. The net force, it's going to be equal to the normal force, and then minus mg, because mg points down. And we just said we pick up as positive, right? Our normal force is assumed positive, it's up. So subtract mg. And so mg, I know the value of it, of course, because I've got a 4 kilogram watermelon. G is 10. So this here is 40 newtons. So then I can work out that the normal force is going to be the net force plus mg, and the values are 1600 and 40, so the answer is 1640 newtons. In a sense, you can think of it as I need a 40 newtons to cancel out the weight, and then the remaining 1600 newtons, they cause the acceleration. It's not 100% so physically right to say it that way, but I think it helps you get an intuition for what's going on in this type of situation. Okay, one last example. Here's the situation I'm going to look at. So I imagine I've got two blocks called A and B, and they're sort of stacked on top of each other on a table. I want to know, well, what are all the forces acting here? So we've got two objects, so for each one we're going to draw a separate free body diagram. Maybe I'll draw the A one over here and the B one over there. So for A, what do we have? Well, A has a weight, right? I'm not giving any masses here, so I'm going to write it as weight m subscript A times g, so it's the mass of A. That's a common convention. If you've got multiple objects, you have m subscript, well, whatever the signifier of the object is. Now, what stops A from falling? If it were just a weight, it would be falling. What stops it from falling? Of course, it's a normal force, Normal force with what? With the table? No, it's not touching the table. It's touching box B underneath it. So the normal force has to be up. So I'm going to write Fn. We know by now I mean a normal force. And that is on A due to B. Right? So it's not block due to the table. It's a block. It's a normal force due to the block, not the table. And that's it. That's it, right? There's nothing else happening with block A. So what about block B? So block B, well, it certainly has a weight too, right? Because it's a physical object with non-zero mass. Right? M subscript B times G. That's my weight. So what's different with A is there's a normal force from the table against the block, and that cancels out the weight. Well, not quite, because there's A on top of it. And we know that block B acts a force on block A, right? It had to, otherwise A would be falling. So that means A is pushing back on B with the same force. Now, I'm going to assume they're the same, like the same mass, blocks A and B, so I'm going to make those two arrows the same, because this arrow is the same as this, and if the same mass means same weight, so they're all the same length. But this is Fn due to, let me write, excuse me, Fn on B due to A, right? And this pushes down because B on A pushes up. Right? So those two are a third law pair, according to Newton's third law. Maybe I'll just connect them up like this and write third law pair. Right? Opposite direction, equal in magnitude. So what's done with the table? Well, that means the table is going to be supporting block B, but its normal force therefore has to be up. It's on B, but due to table, or with the table I could write as well. And so mathematically, what we have is that those two are equal, because they must be, right? They cancel each other out, otherwise A would start moving. This one is equal to this one, because they're two sides of the same interaction. And then this one is equal to the sum of those two. The ultimate result is that just numerically, this one is equal to the sum of the two weights. But the chain of logic is this weight is equal to this, or A would be falling. This is equal to this, because they're the same interaction, just the two sides of it. And therefore this is equal to this plus this, but this is numerically equal to this, numerically equal to this. So the normal force is equal to the normal force from the table on B is equal to the sum of the two weights, mathematically speaking, numerically. Okay. But it's important to note that technically speaking, it is not the weight of A that acts on B. Right? There is a temptation to say that the weight of A acts on B. Not quite true. Technically, what acts on B is the normal force on B due to A. That force, this is the other side of it, happens to be equal to the weight of A, because it cancels out the weight, or else this thing would be falling, assuming there are no other forces acting here. So it ends up being numerically equal, as if we said the weight of A acts on B, but that would be incorrect to put the weight of A here, because the weight of A is a gravitational interaction between the Earth and block A. Right? It doesn't involve block B. It shouldn't be here. The interaction here is between A and B. That's a normal force interaction. But this normal force interaction, that is of course equal to the weight in value. So you kind of get away with saying it's the weight of A acting on B, but it is technically not correct, so don't do it. Okay, make sure, maybe pause the video for a second just to go over what I just said in words. Maybe take some notes while it's fresh in your mind. Okay, now finally, it's been a long video. Finally, I just want to quickly talk about the notion of weightlessness. So here's the mystery about weightlessness. When you say I feel weightless, it might be you're in free fall, right? So maybe you're on some kind of theme park ride where you go up in a tower and you're being dropped, or you're bungee jumping, or whatever it is that you're doing. You feel weightless in the moment of falling. And that is bizarre in a sense, because you're like, wait a minute, what forces are acting on me at this time? Well, actually, it is just the weight, right? That is what it means to be in free fall. So feeling weightless corresponds to actually not being weightless at all. The weight is there and it's the only thing that's there. So what is it that you're actually feeling when you're feeling weightless? Or what is it you're not feeling? Well, here's another example. Or imagine you're in an elevator. And we'll study that in more detail in the next video. Imagine an elevator. And so here you are. And the elevator's starting to go up. Right? The elevator's starting to go up. In that case, you would feel heavy. Right? You'd feel it sort of in your stomach, in your, like everywhere. There's no single place in your body, but your whole body just starts feeling funny. What's changed? Your weight hasn't changed. Right? So that can't be it. Your weight is an interaction between the earth and you. That doesn't change whether or not you step into an elevator. But your weight has not changed. So that's again mysterious. But what has changed? What's kind of different about this situation than like you right now as you're sitting on a chair or a couch or wherever you're watching this? Well, in this case here, right, the weight is the same as always, because the Earth doesn't care, it pulls with the same strength. But if this thing is accelerating upwards, that means its normal force must be bigger up. We'll come back to that in a second. Well, in the next video. In this case here, there's no normal force. Because you're falling, right? Whereas right now, when you're sitting on your chair, you feel a normal force. And that is the key. The key to weightlessness is whether or not there's a normal force on you. So you feel weightless when there is no normal force. No normal force is acting on you. Now, I say normal force, you're like, well, what if I hang from some string or some rope, right? Isn't it a tension acting on me? In a sense, yes. But what you feel isn't the external force that's like pushing against your skin or whatever. What you actually feel is the internal normal forces inside your body. Let me sketch this for you for just a second. So imagine like this is you. Let me give you some knees. There we go, and a foot. Here we go. Okay, here we are running. So late to class again. Waving your arms about, right? And your haircut. Alright, so you're on the ground, right? Now, the ground is acting a normal force on your feet. Your feet are acting a normal force on your ankles. Your ankles on your shin, on your upper legs, on your hip, on each sort of vertebrate going up, right? And in fact, you could zoom in further and say each cell is supporting the cell that's sitting above it. Right? These are all those internal normal forces in your body. Your body is not a point. Right? Your body is made up of lots of different different sections, and we can break them down as much as we want. And we can talk about your kidney sitting on top of whatever tissue it's sitting on top of. And each part of your bone structure is sitting something lower, but really you can go down further and say each cell is sitting on some other cell. And when the floor from the elevator is pushing you up, well then your ankle has to push a bit harder against your shin pushes harder against your knee pushes harder against your thigh pushes harder against your hip, and it is again down to each single cell. And that is what changes. That is the change that we feel. That's why we feel weightless or heavier or lighter, depending on are we going up in the elevator, down, or what's the acceleration of the elevator rather. If you're in a roller coaster, again, we feel it sort of that change internally. If you're weightless, for example, it means we don't feel any normal forces between our cells. So weightless, we feel weightless when there are no internal normal forces in our body. Of course, again, that's some of a simplification, because you've got tendons that are still pulling, different parts of your body are still pushing against each other, but that usual support that each cell gives to the cells above it, to support it, to stop it from falling, those normal forces are suddenly gone. That's what you feel when you feel weightless, even though you're in free fall and there's a weight on you, right? You feel the weight is there, but the normal force isn't there. We'll come back to that idea in the next video. Thank you for watching. I'll see you there.